series circuits again, and we're going to kind of go through some problems and do some things. We're going to kind of try to make this more of a classroom interaction on some, especially in about 10 or 15 minutes. But for now, we're going to pause and let you go through some of these. Mr. Lee? Okay. So what do we know about series circuits? And these are hard and fast rules as far as series circuit goes. So you need to remember these, commit them to memory, and it'll help you understand how these various factors work in a circuit. Current is the same at any point. It matters not where we break that circuit. If we measure current, we're going to measure the same current at any point in the circuit, wherever we break the circuit to measure. Now, when I say break the circuit, current is flow. So just like if we're measuring flow through a pipe, we have to insert a flow meter to measure that. We have to do the same thing. We have to insert an ammeter, and we have to literally break a circuit. Now, in recent years, we've come up with these clamp-on ammeters that are fairly accurate, but don't break the circuit. They do it through some Hall effect sensors and through the magnetic output of the circuit. But especially when we start talking about stuff in the milliamp and microamp, if we want a good accurate reading, when you're measuring 30 amps, an amp or two doesn't make a difference. But when you're measuring 30 microamps, a little bit can make a lot of difference. So to get pinpoint accuracy, we still need to typically break that circuit. If we have multiple loads or multiple resistors, when you see a resistor in a circuit, it could literally mean a resistor. It could mean we've got a circuit board similar to what we've got back here. Grab one of those. Of course, this is one we just practiced on, so it's not really a working circuit. But if this were a circuit board we pulled out of a piece of equipment, that could literally represent a resistor, or it can also represent what we call a load. And a load can be anything that has resistance, that needs power to operate. So when we talk about loads, we could be talking about a resistor, or we could be talking about a light bulb, we could be talking about a motor, whatever the case might be. But when we draw it, especially in series circuits, just to do some evaluation, we're talking about any kind of load, including the resistor. So let's say, for instance, these 4 resistors right here were in series. If we're applying 20 volts across all 4 of those resistors, the sum of the drops across each resistor is going to equal that applied voltage. So if they vary, we may have 2 volts, 6 volts, 10 volts, and 2 volts again. Or if they're all the same, then it comes to mind that they're going to equally drop. So they would each drop 5 volts apiece. So we know that to be a true fact about series circuits. So again, those are 3 hard, fast rules that we can write down and know that that works. The last one being R total is found just by summing the resistors. If we have a 1K, a 2K, and a 3K, we can add 1 plus 2 plus 3, get 6K, and that is the overall resistance of the circuit. So, all right, here's your first one. I'm going to give you a few minutes, and if they happen to come in, I want you to work some, but if they happen to come in, we'll turn it to an interactive. We're going to give you an opportunity to find those values, and let's see if we all arrive at the same answer. I1 and I2 simply means the current through R1 and the current through R2. And those are actually givens if you think about how a series circuit operates. We found a notebook in here the other day. I'm trying to remember who lost it. Keisha Robinson, is she in this class? All right, we'll try to find her in some subsequence.
Takesha?
Takesha.
Oh, not Keisha, I'm supposed to speak since there's two Takeshas.
Yeah, that D-I-K-E-S-H-A. Just a couple more minutes. And somebody asked me today, will we be solving circuits down to this kind of level? Odds are not, but understanding how current flows and how all this works is gonna give you a much greater understanding of electricity. And when you start troubleshooting even systems, it'll become much more apparent, you know, how things work inside of those. So if you can understand this, you can bring it up to the systems level and have a firm appreciation of how things work at a systems level as well as a component level. All right, so what is R total? 30 ohms. And we got that simply by adding R1 and R2, 10 ohms plus 20 ohms equals 30 ohms. All right, how about I total?
3 amps.
3 amps. So we took 90 volts, we divided it by 30 ohms, and our answer is going to be in amps. So that's going to add up to be 3 amps, right? If you don't understand how we're getting to these, don't forget your Ohm's law chart up here, and I'll add it. We've got V over I times R, and we simply cover up whichever one we want. For instance, we need I, that gives us V over R. We need R, that gives us V over I, and V is equal to I times R. So here's the gimmies. What's the current through I1?
3 amps.
3 amps. Current's the same no matter what, right? All right, so that in mind, current through I2. 3 amps. Now, a little more tricky. What is the voltage drop across R1?
30 volts.
30 volts. Voltage is I times R, so we would take 10 times 3. So that would be 10 ohms times 3 amps equals, what do we say? 30 volts. This thing is way out of calibration. It's freaking me out. I'm gonna have to fix that in just a second. I'm writing here, it's actually putting it there. So 30 volts. Now, we shouldn't even have to do the math. Well, we can do a different kind of math. If we're applying 90 and we're dropping 30 across R1, what should be here?
60.
60, but we can still do that math. We can take 20 ohms and we can multiply it by 3 amps, and sure enough, that gives us 60 volts, which is what we surmise by the fact that we understand how a circuit works. The sum of the drop should equal the applied voltage. So we figured that out, but then we mathematically applied Ohm's law again and got the right answer. So yeah, that works, and this circuit pretty well is solved. let's go to the next one. All right, similar situation, got a third resistor. We now know what the I's and the B's. A lot of times you'll see that represented as I and then a lowercase r1, but they're just putting I sub 1, which is really the same thing. While y'all are looking at that, I'm gonna calibrate this screen. Whoops. Okay. That should work much better. Okay, I see bored people, so let's go ahead and work this one out. What is our total?
30.
Yeah, 6 plus 14 is 20, plus 10 would be 30, so 30 ohms. What is I total? 2 amps. Let's talk about again how we got that, because practice is always a good thing. We divided 60 volts by 30 ohms, and that equals, and I'll have to write it down here, 2 amps. So back our ohms off on them, so we did get 2 amps. All right, so what is the current through I1, I2, and I3?
2
amps. Again, current's the same in a series circuit. So those are just there, one, to reinforce that, and two, to make you feel really smart. So, what is the voltage across R1?
12.
All right, so we say 2 amps times 6 ohms equals 12 volts. Again, it's simple, ohms off. How about the current through across V2? I mean voltage across V2.
28.
All right, so 2 amps times 14 ohms, 28 volts. This thing's finally writing 28 volts. And again, we could add those two. 12 plus 28 gives us 40. I don't have to apply ohms law if I've done everything right. I can go ahead and say that's got to be 20, but we can also do math. 2 amps times 10 ohms equals 20 volts. And if we add up 12 plus 28 plus 20, that gives us 60. So we improve our circuit once again. Okay, next. Now these things you see here, just to explain, this represents a voltmeter measuring across this resistor. This represents an ammeter inserted in the circuit, and this represents a voltmeter placed across the source. So when you look at this, they do actually become part of the circuit, but they're just measuring instrumentation that's inserted either across for the voltage or into the circuit to get current. So our actual circuit is still drawn pretty much like we would expect to see, except we've got some measuring instrumentation attached to it. And we can literally put a circuit out on a proto board and hook up these meters and do the exact same thing we're doing here. We can arrive at some things a couple of different ways in this circuit. I like this circuit because it lets us start kind of applying some of the things we should know already. What is our applied voltage?
75.
And what are we measuring across R2 according to our meter?
25.
So what is our voltage across R1?
50.
50. If we subtract the 25 that we're measuring across R2,
They're on the way.
okay, thank you. That leaves us 50 volts. Now we can assume that, but let's see if we can find it using Ohm's law. Well, we know R1 is 10 ohms. We know we've got 5 amps through R1. So remember, it is I times R, so 5 amps times 10 ohms equals 50 volts. So we deduce that by the fact that we subtracted 25 from the 75, but we can also take our other givens and arrive at that just by using Ohm's law. Now what is the current through I2?
5.
5 amps, because we're given that. And remember, the current at any point, and we didn't make this slide, that would be a capital A in the real world. We don't usually use a lowercase a for amps. But yeah, 5 amps is anywhere in this circuit. We could literally break that circuit, install an ammeter right here, and measure 5 amps. We could break that circuit right here, install an ammeter, we're going to read 5 amps. It really does not matter where we break that circuit, we're going to get that 5 amps. All right, how about R2's value? That's going to be a little more complicated. What do we get for that?
It's going to be 5.
How much?
5 ohms.
5 ohms? So how'd you get that?
Ohm's law.
Ohm's law. We know current, so if we go back to our Ohm's law, it's V over I times R. We know the current through R2, it's 5 amps. We know R2's value, R2's voltage So we can take that 25 volts that's across R2, we can divide it by the 5 amps, and that's going to give us the ohms, which is 5 ohms. So now, if we've got that, we can even double check some other ways. What is resistance total? 15. So if we say RT equals 15 ohms, what is IT? 5 amps, right? So if we divide VT, which is 75 volts, by RT, which is 15 ohms, we're going to get 5 amps, which is the current we're seeing. So that's the beautiful thing about Ohm's law, is it allows us to check and recheck and understand that what we can sometimes surmise pretty easily, we can prove mathematically using that formula. So again, it just gets down to taking what we know and understanding how it works and applying it across the circuit. All right, let's go next. Okay, let's talk about this one. What is the voltage across R1? 25 volts. So let's talk about how we got there. Now all we're given is the current in the circuit and the resistance of each resistor. Well, Ohm's law says if we want to know voltage, we multiply I times R. So R, or I, is 5 amps. R is 5 ohms. So that's going to give us 25 volts. So that's where we can arrive to R1. So we know that to be true, so the same thing can be applied to R2, correct? So again, 5 amps times 15 ohms equals what? 75 volts. All right? So what is voltage total then? 100 volts. The sum of the drops, 25 volts plus 75 volts, should give us 100 volts. So let's see if we go back and apply good old Ohm's law, if it really works. What is R total? 20 ohms. What is V total? So Ohm's law says 100 volts divided by 20 ohms gives us what? 5 amps, and that was a given, and that does match the given that we were given. So again, Ohm's law will let us understand and backtrack and verify that our answers are correct. And I don't know about y'all, but I like having ways to kind of double check my work. And that's one way to do it, is what we just did. All right, next. I see important people. All right, so let's move on. Try to answer this. What is R total? 10 ohms. Again, we can know that the sum of the resistors in the circuit, 5 plus 3 plus 2, will give us 10 ohms. What is I total?
2 amps.
2 amps. And I'm going to go back here. I don't know if I erased it or if it stayed on the slide. But yeah, we take I total, we take applied voltage divided by R total, so 20 divided by 10 will give us 2 amps. All right, so what is the voltage drop through R1 that we see? 10 volts. Again, right back to Ohm's law, voltage is equal to I times R. I is 2, R is 5, 2 times 5, 2 volts. 2 amps times 5 ohms gives us 10 volts. That's not embarrassing at all, but easy to do. All right, how about V2? 6. 2 times 3 is 6, and that is volts. I'll get that right this time. And R3? 4 volts. So the sum of our drops should equal our applied. 10 plus 6 plus 4 does get back and equal 20. We've got R total, and we arrived at our I total, so we pretty well solved that circuit. So let's go to our next. I'll try to leave that up there for mistake. We'll redraw it each time. Hey, we'll redraw it each time. I thought it stayed on the board. It stays with the slide apparently. There's one of those we should be able to solve straight out of the gate. Which one is it? V1. We've got an applied voltage of 40 volts over here. We're dropping 10 across R2. We're dropping 20 across R3. What does that leave for R1? 10 volts. So the voltage across R1 is indeed 10 volts. So now we can go back and figure some of these others. We've got voltage here, and we've got resistance. What can we get with that? Current. So we take 20 volts and divide it by what? 10 ohms. That equals how much? 2 amps. So what is the current through I3? 2 amps. What's the current through I1? 2 amps. Current's the same no matter where. So now it's asking us for the values of R1 and R2. Well, R3 equals 10 ohms, So how are we gonna calculate R2? What two things do we know for R2? We know the voltage, which is 10 volts. And we know the current, which is 2 amps. So what does that put R2 as being? 5 ohms, right? And I could have went with R1 first, it really didn't matter. All right, we've got, I'm sorry? Same thing. So what do we know about R1? We know it's dropped, right? It's going to be 10 volts divided by 2 amps, which equals 5 ohms. So we can still, one more way to check, we can take I total, which is 2 amps, we can divide it into our source voltage. What's 2 amps excuse me. We can take R total, which is what? R1 is 5 ohms, R2 is 5 ohms, and R3 is 10 ohms. So if we add 5, 5, and 10, what do we get? 20 divided into 40 gives us what? 2 amps. So this 2 amps that we're seeing here and here is the same 2 amps that we're seeing throughout that circuit. So again, we can take what we know regarding the laws of a series circuit, and we can apply it across, and we can make some observations. All right, let's go to the next. All right, a little more complex, laid out a little different. And what did we say about ET versus VT? Same thing. And what they use in Europe to represent voltage. Remember that? What letter? U, that's right. So, give me just a few minutes on this one, then we'll work through it together. You can.
Folks, I want to introduce everybody. This is Andre Swantik, president of Environmental Glass for all companies. This is Talus. I can't remember your last name, but I probably couldn't pronounce it if I did. So, and then Brandon Durden, and Brandon's from actually Sandersville, so he speaks it all right. But
He speaks a little bit English.
yeah, a little bit. He actually speaks redneck. So. Yeah. So anyway, I'll give Mr. Swantik a chance to say what he wants to say, and if you have any questions for them, now's a good time to ask. And we can go to the next class, or would you like me to bring those over here?
We don't want to interrupt too much. I mean,
Okay.
we will also learn in a very short period of time. If you have any questions, please ask me. I didn't prepare the big speech. We are not talking too much over in Europe. But I'm very happy to see so many good people here, and I wish you all the best, and give your best, because we really need good people. We have equipment which is very, very expensive, and also, if you don't deal with that correctly, dangerous. I mean, a melting tank, I don't know if you was already going so far, if you saw pictures. We are working with temperatures 2,500 to 3,000 F. If you put your finger in, it's gone. It's like a volcano. And that is why we have to really have people which know what they're doing. Thales, for example, he's our project manager here for the US project. You are working now with us 5 years?
5 years.
Yeah.
Will be 5 years.
5 years. You can see we are a pretty young team. I'm one of the older guys with my 34 years old.
We'll go with that.
But very, very important to us education, because we are only as good as our people. But the company can be only as good as our workforce, and you at the end will let it happen, will make it happen. We only can lead you. Yeah, and that's why education for us was one of the most important points, beside the money. To build this, what you see here, it's only money. Not more and not less. A lot of people have money, but we have to get life into. And this is with you. education for us is very, very important. Anybody have questions? Please feel free.
Now's the time to ask it if you got one.
No question? I come back in 2 months and you have a lot of questions.
5 minutes after.
We'll have time right now.
Oh, yeah, after you leave, I'll have plenty, yeah.
Can we leave this picture here, then you can see what will happen here?
Actually, the class can come in and make it done, or look at the rest of this.
The building company will start now in the next couple of days. Yeah, and the plan is now that we are heating up the furnace. It means we start to put temperature in the furnace 1st of November next year. And that means we have the first fiberglass 1st of December next year.
How long does it take the furnace to get up to 10?
1 month.
A month?
You have to imagine this is very high, dense press material what we are working with. This refractory material has such a high density. If you would put very fast temperature in, would give a big explosion. The same way on the other way around. If we lose, for whatever reason, much temperature, same thing. Yeah, this is the complexity of the furnace. That's why we're heating up the furnace. The chrome material tells me, you have to correct me if I'm wrong, 2 degrees every hour. Celsius, 2 degrees Celsius every hour. Now you can calculate how long we need to come to 1,600 degrees Celsius. That takes a while. But the good thing is, for all the mechatronics, for the maintenance people, we will have already for how much we have in total? For 50 people.
Yeah.
For 50 people, we will have jobs to implement the technology, which will approximately start April next year, March, April next year. That means we will give a lot of you guys already the possibility to install equipment. And to install equipment means to get a good education already live on stage. After that, the good thing is we have then, of course, the course here will be finished end of August. Yeah, August 31st. Then we have September, October, for a lot of you guys go to Europe, either to Germany or to Latvia to get on-site training. Yeah, because it's also important for us. Because this furnace is the biggest we ever built. And very important for us that the startup going as smooth as possible, because we will produce 120 tons, metric tons per day. That means, what is it in pounds, 260,000 pounds per day. We don't want to have too much waste. Yeah, and waste is happening if people don't know what to do.
And I went back up when he says waste. He told me in Latvia, that's where he started, taking out the trash.
Yeah. I started with this, not in Latvia, but in Germany. This is one of the not nice jobs we can offer.
Yeah, no kidding.
Yeah, no kidding, no kidding.
I spent quite a few years as a janitor.
Okay. This is what I was starting with.
In the event you have trouble with your furnace, what's your cool down cycle?
Excuse me?
In the event you have mechanical problems with your furnace, what would cool down cycle be before you can
We
start?
don't talk about this, it can never happen.
You run.
The cooling down, I mean, this is, if this happens, it's waste. The whole furnace is history. This happens exactly every 8 to 10 years, it's depending how good you will treat the furnace and how good the temperature regime will be handled. That means minimum 8 years, maximum 10 years. Then we will stop the process, leave the glass out. And this furnace, approximately 3 to 4 days, we let it cool down. And then it will be already, the refractory will be knocked down. And it's still hot. It is still hot, people go in there. There's special people we using in protecting clothing and knock it down. And then we build it up. The furnace repair for this size of a furnace is approximately 2.5 months. And then another 10 years. And for us, doesn't matter crisis, no crisis, Easter, Christmas, We're always working, never stop. I'm now 20 years in the company, we was never ever stop. Even in 2009, which was a tough year.
Where do your raw materials come from?
From this neighborhood, we will maybe knock the house down and send it because we're staying on top of a lot of kaolin. Kaolin is a big material as our aluminium input. We are working with limestone and we're working with silica sand. These are the three biggest components for our glass. Of course, they're coming some other oxides on top of this, but it would go too far to explain all that in detail. This mixing station is fully automatized. Trucks coming, pumping it in, and the mixing is completely fully automatic. Nobody need to go by hand. So.
What kind of shift schedule is it gonna be running?
We have 12-hour shifts.
12 hours?
This is, we don't like that too much, I tell you openly, but unfortunately our people like it. Because you work 1 week 3 days, the other week 4 days. Because 12-hour shifts, I mean, if I work 12 hours, I'm very tired. And I don't need to work with my muscles, and it's tough. I would prefer 8 hours, but our people always have a strong argument to work in 12 hours. In Latvia, we work in 12-hour shifts. Here we are working, we started with 8-hour shifts, we are changed to 12-hour shifts. But this is at the end what we will make very democratic. We will ask the people what they prefer. Yeah, up to now, everybody, we had a 99% vote for 12 hours.
Is that 2 shifts?
We have 4 shifts.
4 shifts?
We have 4 teams, it's 2
Okay.
shifts, you have a 7 A to 7 P and a 7 P to 7 F. And they're rotating swing shifts, you'll work a day shift, a couple of days, have a couple of days off, come in, work a night shift, a couple of days off, come back a day shift. So it's rotating swing.
Every other weekend.
Okay.
How far you are driving or to work to Dublin? What is the average distance? Coming all from Dublin or?
I don't know about them, but I come from Adrian, so I got 37-mile trip.
Okay.
I'm about 30 miles.
Okay. I mean, economical for your briefcase, 12-hour shifts are more interesting. But it's up to you. I mean, we recommend 8 hours. Unfortunately, our people want to have 12 hours. And as long as you can bring quality in 12 hours, I'm fine with it.
Anything else? Y'all asked some good questions. You're making us look good.
Thank you very much and good luck.
Thank y'all.
Hope to see you soon. Thank you.
Good information there. Let's jump back in. Let's take our knowns. What is the first thing over here on the right-hand side we can fill in?
Current.
Current. Yep, we can fill in current. We can also fill in RT, but it's not there, but we could. So current is what? 0.5 amps. All right? So, if we go ahead and add RT, which will help us find ET, what is our RT? 100. 10 plus 10 is 20, plus 50 is 70, plus 30 is 100. All right, now we want to find ET or VT. So we've got IT and we've got RT, so what do? We multiply, we say I times R. So in this case, 0.5 amps times 100 ohms.
200 volts.
Would be 50. If we divide, it would be 200, but it would be 50 volts. So 0.5 times 100 would give us 50 volts. All right, so now, the rest of this should be pretty easy to us. We know the current through each one, And if we know the resistance, how do we get the voltage?
Multiply.
Multiply. So it'll be 0.5 all the way down. Then we just gotta multiply by each resistor, right? So it'll be 10, 10, 50, 30. So what's 0.5 times 10? 5 volts, right? What is 0.5 times 10? How about 0.5 times 50? 25 volts. 0.5 times 30? Let's add them up. 25 plus 15 is what? Plus 5? Plus 5? 50. So 50 volts equals 50 volts. We've already got our IT, we've got our RT, everything proved out. All right, next. Okay. Now, we've got some givens on the right-hand side, so if you don't see it in the schematic, look to the right and you'll find some things that are there. I think there'll be in some future ones that you won't see those values necessarily on the schematic. Okay, so what can we find straight out of the gate here?
R2?
RT. So we've got ET or VT, depends on which one we call it, and we have IT. So if we take 90 volts and divide it by 3 amps, that gives us what? 30 ohms. So, our total is 30 ohms. Now we're given R1 and R2, we can do the math, and what would that make R3? 15 ohms, right? But, we're not given enough information beyond that, so we have to surmise that. We're not given any other values. So yeah, that should work. All right, well, how about the voltage across R1?
15 volts.
15 volts. Again, it's gonna be 3 amps all the way down. It's gonna be times the value of each resistor, which is 5, 10, and we came up with 15. And if our sums add up to our applied, then we must have our circuit right. So what's 3 times 5? What's 3 times 10? 3 times 15. All right, if we add 15, 30, and 45, what do we get for our applied voltage? Is that indeed what we had? Yep, so it worked out. I keep erasing this board, but now that I've discovered it goes with the slide, I don't have to. I learned something today too. All right, so again, the applied values, what you're given is to the right. There's one special note on this one, right there at the very bottom. It's gonna make everything clear, hopefully. And it says R1, R2, and R3 are all the same value. And that should lead you to something straight off the bat. Look, think back to the rule, the sum of the drops equals the applied voltage. And if we have the same value resistor, what's going to be true of our drops? They're going to be the same, or divided equally between each of those, would be a better way to essentially say. We'll see a common theme in this moment. Didn't intend it that way, but it worked out really well. So tell me, what is the voltage drop across R1? 15 volts. What's the voltage drop across R2? 15. What is the voltage drop across R3? 15. The sum of the drops equals the applied. We know the applied is 45 volts. We said they're all the same value. If they're all the same value, that drop is going to be distributed equally. And it doesn't matter if that value is 10 ohms, 100 ohms, 1,000 ohms, 1,000,000 ohms. If we're applying 45 volts and they're all three the same, they're going to drop an equitable amount or divisible by 3. All right, so now we know current, now we know voltage. We can get the resistance. What is the resistance of R1? Or what is total resistance? 15 ohms. So what is the value of R1, R2, and R3? 5. Yep, we know they're equal. 5 ohms. So there we go. So again, if we go back to all our Ohm's law and check it, recheck it, we'll arrive at the same thing. All right, here's one a little different. We're given R1, we're given R2, we're being asked for R3. Excuse me, we've got R total, and we've got a voltage drop across R1 only. So, I'm gonna give you a few minutes on that one, because that changes everything a little bit. So what is R three?
60
60 ohms. And how did we arrive at that? Right, the sum should be equal. All right. Are we missing something? Or do we have everything we need? We got our total. We've got the voltage across R1. So if we know the voltage across R1, we know R1's value, what can we get?
And the
Current. Current is what? 2 amps. It's V, which is 50. Oh, excuse me, yeah, divided by R, which is what? 25 ohms. So I total is equal to 2 amps. So that means because we've got 2 amps here, we've got 2 amps everywhere, right? So we can start filling in some blanks here.
2 amps times 100 ohms.
2 amps times 100 ohms is what?
200 volts.
200 volts, right here?
But,
Oh, total, yeah, I'm sorry. 200 volts. All right, now what? We got R2's value, we got R2's current, so again, I times R,
2 times 15, 30.
30 volts, right?
2 times 60 would be 120.
2 times 60 would be 120. 120 plus 30 plus 50 gives us what? 200 volts. What was our applied voltage? Works. Some pretty math. All right, we'll do one more, and we'll actually work through it. And I think at that point we'll take a break. I can tell you already. I didn't learn it long. I'm sitting here erasing. Old habits die hard. All right, so we're given, and shame on me, IT should have been expressed 0.5 amps, not just 0.5. And this should have the volts, this should have the volts, and this should have the volts. But other than that, it's beautifully accurate. What can we get right away? Voltage across R2, right? What is the voltage across R2? 140. We said we had 200 volts applied. We're dropping 10 across R1. We're dropping 50 across R3. If we subtract 60 from 200, that leaves 140. So now we have the current through every resistor right here. That applies to everything. So we can start getting, we know the voltage drops across each resistor. So it's literally going to be 0.5 all the way down times 10 times 140 times 50, right? 0.5 times 10, 5. 0.5 times 140, 70, and 0.5 times 50, 25. Let's see, wait a minute, did I do it wrong? Bad instructor. R is equal to V divided by I, right? Y'all were letting me roll. So, it would be 10 volts, 140 volts, 50 volts, divided by 0.5. Now we're gonna get double our number. 20 ohm, 280 ohm, 100 ohm. So let's get our total just for grins and giggles, which is what? 400 ohms. We have I total of 0.5. We divide 400, say I times R, 400 times 0.5. That gives us 200, right? So again, Ohm's law works to do divided by instead of times. So let's take a break till about 20 after, and we'll cover some of the things we did with the soldering. We'll finish some of this program tests. Here is what we call a simple parallel circuit. There are no series resistors in this. This is just a pure parallel circuit. Everything in your car, everything in your home is parallel. Now the difference is there are some 120 appliances and there's some 240 volt appliances. And in your car, everything runs off 12 volts. Every load you have in your car operates off 12 volts. Virtually. There's some exceptions, we shall not cover those. So, what happens here? What is the voltage drop across R1?
5.
5 volts. The voltage drop across everything in your car. Dome light, 12 volts. Headlight, 12 volts. Radio, 12 volts. Everything is in parallel. Everything is across the source voltage. So everything will drop 12 volts. R1, if I took a meter and I measured right here, across that battery or whatever that source voltage type of thing is, what am I going to measure? What is the electrical? Now, this symbol means ground. That basically just means everything's connected to ground. So it's the same as drawing that right there. What is the difference electrically between that first point and these points?
Nothing.
Absolutely nothing. Electrically, this is the same as that, this is the same as that, so I'm going to measure 5 volts right across here. If I slide over, what is the difference electrically between this point and that point? They're the same, and I can work it over to the third and I'm going to have the same answer. So everything that's in parallel, whatever voltage one resistor sees or one load, the other two are going to see. So this guy is seeing 5 volts, this guy is seeing 5 volts, this guy is seeing 5 volts. Now, what do you think in series, we added all those resistors together. What do you think happens in parallel? I like it in the cricket shirt. That means we actually teach them something.
You don't have them.
You don't add them. They actually decrease the more you apply. And what happens is, there's this nice formula, and I'm going to bring up a slide, see if I can figure out how to do it on the board. Well, draft, let's just go over here to the computer. Then I'm going to show you something that will make your life much easier. far as these parallel circuits, if you have a calculator, and the ones calculator do this, you just have to be very careful about inputs. So if I've got a supply out here, it's 12 volts, and I put a resistor, I call R1, and it's,
100.
10 ohms. Not hard to figure the voltage drop across R1, right? 12 volts, right? Pretty easy. But if I had another resistor in parallel, and it's 20 ohms, what is the voltage drop across R2? 12. Same thing. Electrically, this point is the same here and here. This point is the same here and here, so it's 12 ohms. And we know resistors don't add, it's not 30 ohms. The formula for resistances in parallel is 1 over RT. Wondered how we were going to use this math? Here we go. 1 over RT equals 1 over 10 plus 1 over 20. So that formula is literally, if you write it out, 1 over RT equals 1 over R1 plus 1 over R2 dot, 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 to 1 over R, whatever the last one is. So
Infinity.
if you have 500 resistors, you literally have to do 1 plus, reciprocal. So what you do is, let's find the common denominator. What's the common denominator between 10 and 20? 20. I did that on purpose. It's late today and I didn't want to have to math it hard. All right, so what does 1 over 10 become? 2 over 20 plus 1 over 20. So 1 over RT equals what? 3 over 20. Now, there's a magic little secret that we learned. I'm going to erase, I'm going to come up here. If we have 1 over RT equals 3 over 20, this guy pointed it out, but he's not in his normal spot. Where are you? There you are. You mentioned it. We can reciprocate both sides, and it's going to be the same. And I'm going to prove that to you mathematically, but I'm going to go ahead and do it in front of your very eyes. We can say RT over 1 equals 20 over 3. RT equals 6.67 ohms. Now you might be asking yourself, how can we flip those mathematically and it works? Let's go back to it. 1 over RT equals 20 over, whoops, wrote it back. I'll flip one side, 3 over 20. First thing I'm going to do, remember it's an equation. As long as we keep it equal, as long as we keep the scales balanced, as long as we do whatever we do to one side. If I got 5 pounds over here and 5 pounds over here, they're the same, right? If I had 10 pounds over here, how am I going to equate the other side? Whatever I do to one side, I have to do the other. I have to keep it equal. I don't have to keep it the same value. I have to keep it equal. So, let's multiply both sides times 20. And 20 is really 20 over 1, right? So if I multiply both sides by 20, that cancels out. So we come out with 20 over RT equals 3, right? With me so far?
Can't we just press the reciprocal button on the calculator?
Good.
Let it
I'm
do
just
it
trying to
first.
show this math. Now I'm going to multiply both sides by RT. I'm going to say times RT, and I'm going to say times RT over 1. This cancels out. We come out with 20 equals 3 RT. Now what can I do?
Divide 3.
divide 3 into both sides. I come out with 20 divided by 3 equals just RT, right? Because if I divide 3 RT by 3, this cancels out. So we come up with 20 over 3 equals RT. We can rewrite it with RT on this side. Equals 20 divided by 3 equals 6.67 ohms. So which would you rather do? Do all that math or just simply reciprocate both sides? That right there makes life a whole bunch easier. So that's what you want to do. We mathematically proved we're going to get the right answer. You can go through that long form way of getting there. And I could have done some different division. I could have done some different multiplication. It's always going to work out mathematically. We're reciprocating. Because basically what we're saying is 1/2 equals 2/4. If we reciprocate both sides, it's 2 over 1 equals 4 over 2. Works. 2 over 1 is 2, 4 over 2 is 2. So again, we can reciprocate all we want as long as we do both sides. All right, let's add a third resistor now. And if you notice, let's go back to that one for a minute. I didn't point this out. We had a 10 and a 20, right? What was our overall resistance?
6.67.
6.67. In a parallel circuit, total resistance will always be lower than the lowest resistance. So if we didn't get an answer lower than 10, we mathed wrong. It may be 9.999985, but it's going to be lower than 10. It may be so close to 10 that it looks like 10, but if you got a calculator long enough, it's going to be lower than 10. So it's always going to be the lower than the lowest. So let's start with this one. And that's why I had to change the answer to number 9 a while ago. We'll get more of that coming up. All right, 20 volts. We got R1, 10 ohms, R2, 20 ohms, and R3, I know you're thinking 40, but no, it's going to be 80 ohms. All right. So now I would have to literally, to get resistance, I would have to say 1 over RT equals 1 over 10 plus 1 over 20 plus 1 over 80. What's my common denominator? 80. So 1 over RT equals 8 over 80. Plus 4 over 80 plus 1 over 80. So 1 over RT equals what? 13 over 80, right? All right, so let's flip everything. It'll be RT over 1, so I'm just going to simply write RT equals 80 divided by 13. It's got to be lower than what? Lowest, which is 10. Or we math wrong. So what is 80 divided by 13? Who's got the calculator out? Sir? 6.15. 6.15 ohms. So we don't know that we got the right answer for sure, but we know we don't potentially have a wrong answer. We come up with 16.15, we math wrong. Has to be lower than the lowest. But as long as we come up with something lower than the lowest, we can potentially say that we mathed correctly. Now, I'm going to show you a calculator shortcut. I know nobody wants to know a way to do that easier, but I'm going to show you anyway. On the Windows calculator, we have a reciprocal button. Does anybody know which one it is?
1 over X.
It is the 1 over X right here. That is the reciprocal button. That, when you're doing parallel equations, is going to be your friend. And imagine even having to punch all this into a calculator and do it, it gets kind of hinky, right? Watch this. I'm gonna put in the value, I'm gonna reciprocate it, which is what I'm saying here. I'm gonna add it to the next value, the reciprocal of the next value, and I'm gonna add it to the reciprocal of the next value. I'm gonna total it. If you don't remember to total it, you're gonna get a wonky answer. You'll get a wrong answer. So I got 10, 20, and 80, right? 10 reciprocal plus 20 reciprocal plus 80 reciprocal. If I don't total it, it's all over but the crying, equals, and now I'm gonna take the reciprocal. There's your answer. 6.15. So let's do that again. It doesn't matter which order. I'll take 80, I'll reciprocate it, plus 20, I'll reciprocate it, plus 10, I'll reciprocate it. I'll press equals, and then I'll get the reciprocal of that, 6.15. And all I did was exactly what I did here. I did 10 reciprocal, 20 reciprocal, plus 80 reciprocal. I added 10 reciprocal, plus 20 reciprocal, plus 80 reciprocal. I got the result, which is the 1 over RT, then I reciprocated that, and I got the answer. So that makes it a whole lot easier than having to do all that long math. So while that sheet's going around,
What color's the grass in Trenton again?
so we've got RT. What can we find if we have VT, which is 20, and we have RT, what can we find? IT, that works the same. So what will we do? So we divide 20 divided by 6.15, right? 3.25. Now what do you think, where do you think we have 3.25 amps at?
Everywhere.
Everywhere.
No, before and, come on, man.
You already,
I know.
right, we have it, we do have it in a couple of places. Where do we think we might have it? Yeah, right here, we've got 3.25 amps. But then, remember, current, just like water, if it's got more than one path to flow, it likes to find other ways, right? So what's gonna happen is, some of the current's gonna go, hey, I'll go through R1. That lined up too long. Then some of the current's gonna go, well, if you're going that way, I'm gonna go this way. It's gonna come here. And then last but not least, some of it's gonna say, I'm running out of colors. Some of it's gonna say, well, I'll come here. So what we have is we have some amount of current going through R1, some amount of current going through R2, and some amount of current going through R3. And that makes sense when we think about it. In your car, do you think your dome light draws as much current as your headlights? Of course, yeah, exactly. So when you turn it on, you're blind if you got one of those. No, your headlight's drawing a lot more current. So same 12 volts, but there's a lot less current going through that dome light than there is those headlights. Those headlights are a lot lower resistance that give you that brighter light. That dome light's the higher resistance. It gives you a light that won't make you run off the road when you turn it on. I was driving a Domino's pizza truck when I was about 25 years old, a part-time job, and I was a city boy and never seen a Q-beam spotlight. There was one laying in the seat. And I turned that thing on, and holy cow! It like to have been a wreck, Domino's pizza truck. So, all right, good. So everybody's got the sheets, right? So what we're finding out is current splits through each one of these. Well, guess what? We know the value of the voltage. We know the resistance. We can find the current. It's right before our very eyes. I R1, I R2, I R3. So what is voltage of R1? 20 volts. What's voltage of R2? 20 volts, same for R3. So we can say times 10 ohms times 20 ohms times 80 ohms, and we can get the current for each one. So what's 20 volt? I did it wrong. Should be divided by. It's okay, y'all can correct me. I'm married, I'm used to it. Sorry, Tracy. So what is 20 divided by 10?
Green.
Right, it'll be what? 2 amps right here, right? 2 amps coming down through R1. What is 20 volts divided by 20 ohms?
Blue.
1 amp, right? 1 amp coming down through this guy. And what is 20 divided by 80?
Aliens.
Huh?
0.25.
0.25 amps coming through here. Well, looky there, would you? Right here, where you said we had full current here, we've got 3.25 amps flowing. 2 of it gets here and says, I'll go this way. 1 of it gets here and says, I'll go this way. And then 0.25, 2 plus 1 plus 0.25 gives us 3.25. So here's the rules for parallel, and you'll get them later. Voltage is the same, as long as we're talking about simple parallel. Now we're going to throw, just like we throw some letters into math, we're going to throw some kinks into this. But in this type of circuit where there's one load in parallel with another, they're all going to see the voltage, same voltage. Voltage is the same for each resistor. Current splits, but the sum of the currents through each branch equals to I total. Third rule, R total will always be lower than the lowest resistance. Always. Always, always. Now that can vary a lot, and I'll show you one more and we'll do just the resistance and I'll let you go. But we'll have 20 volts, and we're going to have 10 ohms, and we're going to have 5,000 ohms. What is our total going to be? Less than what? 10 ohms, right? So we can apply the 1 over RT is equal to 1 over 10 plus 1 over 5,000. What's the quick common denominator? 5,000. 1 over RT, got to multiply this one times 50. So that'll be 50 over 5,000 plus 1 over 5,000. 1 over RT equals 51 over 5,000. We can reciprocate that and say RT equals 5,000 over 51. So somebody with a calculator, do that math for me.
98.04.
It's, did I math wrong?
Yeah, 10 going to 5,000.
500. Yes, I did. See, as soon as she said that, I knew I math wrong because I got 98. And it's got to be less than 10. So I have done some math incorrect. So let's go back and correct my mess up. And then we'll recalculate this puppy. So a perfect example of why, if we know that rule, we cannot get caught up. So that's 500 over 5,000, right?
Yeah.
Instead of 50 over 5,000. So that gives us 1 over RT equals 501 over 5,000, not 51. So now, we'll say RT equals 5,000 over 501. What does that math out to be? 9.98. Barely lower than 10, but nevertheless lower than 10. It'll always work out. We can calculate that same thing. We'll bring up the calculator. We can do it with just 2. We can do it with 100. So we can say 10 reciprocal plus 5,000 reciprocal equals reciprocal 9.98. Which one's gonna have the higher current? This one or that one? 10 ohm or 5,000? 10 ohm. The closer we are to zero, the higher the current. So the 10 ohm is gonna have much more current than the 5,000. That's your headlight, that's your dome light. For lack of a better description. Don't worry about having this today. This was that 2-minute trailer. We're gonna have plenty of time to work this. Some of you are kind of wanting to get a broad spectrum idea of how this works. We just put the devil in electronics by parallel, and wait till we get to serious parallel, but we're gonna increment this slowly, so you're not gonna, we're not taking the training wheels off yet.
I don't know, after seeing the trailer, I think I wanna skip the movie.
Y'all are dismissed.